lecture is the introductory lecture for Chapter 3. And Chapter 3 is all about what are called linear systems of differential equations. We've looked at systems of equations before, even back to Chapter 1, but especially in Chapter 2, and the focus was on numerical and graphical ways of understanding systems of equations, both linear and nonlinear. Euler's method can be used in two-dimensional and even three-dimensional case to understand systems of differential equations. You can also just rely on the software that we have that comes with our book to understand them. And a key concept there was the concept of a vector field and the corresponding direction field as the way to provide geometric insight into what's going to happen in the phase plane or the phase space. I'm going to write down a system of differential equations. dx dt equals negative 2x minus 2y, and then dy dt equals minus 2x plus y. There we have a system of first-order differential equations. As we saw in Chapter 2, it's helpful to think of this in vector form. The system is a group. We're not really thinking of these equations individually by themselves. We're thinking of them as a group. And one thing the vector perspective does is it allows us to think of them as a group. It makes that formal in a sense. We can take this system of two scalar equations and write it as one vector equation. And I'm going to write my vectors as column vectors. Sometimes we do that. Sometimes we write them as row vectors. The book often does that. There we go. So the system of two scalar equations has become one single vector equation. And we then often write this in vector form. If I were going to write this vector in vector with vector notation, it's the derivative of capital Y vector, where capital Y is the vector whose components are little x and little y. I'll put that over on the side here. Capital Y is a vector whose components are little x and little y. And there's its derivative. Just differentiate each component with respect to t. And on the right-hand side, well, that's a vector-valued function of little x and little y. It's really a vector field. I'll emphasize that the output is a vector by writing f with the vector symbol above it. And the input I could write as x comma y. I could write it like this, or I could write it as capital Y, the vector capital Y. All it is now is it's just a convenient way of writing the system of equations. Although, like we saw in Chapter 2, based on this convenient way of thinking about systems of equations as single vector equations, we can jump from this to that vector field and the corresponding direction field based on the idea of what a vector and what a vector field is. Today, we're going to focus on the fact that this is a linear system. You see only first powers of x and y on the right-hand side. No x squareds, no x times y's. And in fact, there are not even any constant terms. Some people call equations with constant terms linear, but in Chapter 3, we definitely don't want constant terms. Okay, that's going to mess up our theory if we deal with constant terms. We can adjust it to deal with constant terms, But we want to focus on the basics right now, so we're not going to have constant terms. What I'm going to do now is I'm going to think of this vector, negative 2x minus 2y for the first component and negative 2x plus y for the second component, in another way. I'm going to create something called a matrix, which many of you have heard of before. In fact, a 2 by 2 matrix that contains the coefficients of the x's and y's in the order that you see them right here. So the first coefficient up here, the coefficient of x is negative 2. I'm going to put a negative 2 right there. The next coefficient, the coefficient of y, is negative 2. I'm going to put a negative 2 right there. In the second component, the first coefficient, the coefficient of x is negative 2. And the second coefficient, the coefficient of y, is positive 1. And then I'm going to put the vector xy to the right of that. Now, if you've never seen matrices before, or even if you've seen matrices but you've never done matrix multiplication, you may wonder what this means. Right? Well, here's what it means. This thing is a matrix. It's a 2 by 2 matrix that we're going to call A. And this thing really is the same as the vector y. The way we're thinking of this, algebraically speaking, is as a multiplication. You can multiply a 2 by 2 matrix times a 2 by 1 column vector. As long as this first 2 for A is the number of rows it has, 2 rows. The second row, number 2, is the number of columns it has, also 2. For this column vector, it's got 2 rows and 1 column. And anytime you have, we can think of these as both as being matrices. Anytime you have the number of columns of the matrix on the left equaling the number of rows of the matrix on the right, you can do what's called matrix multiplication. Or in this case, we might call it matrix vector multiplication. And here's how you do it. Thinking in terms of notation, words you may have heard in a physics class before, we can focus first on this first row of the matrix, negative 2, negative 2, and imagine that as being a vector, written as a row vector. And imagine taking the dot product of that row vector with this column vector. If you've never heard the phrase dot product before, well, you should look it up in the book or look it up on the internet. But what you do is you multiply the first components of the vector, of the two vectors, and then add the product of the second two components. So I'd have negative 2 times x plus negative 2 times y as the dot product of this row with this column. And that's exactly what we have here, negative 2x minus 2y, for the first component of the vector field. And to get the second component of the vector field, you take the second row of the matrix A and take the dot product of it with this column vector right here. So we have negative 2x plus 1 times y, which is exactly what we have right over there. Turns out when you do matrix multiplication, the resulting matrix you get always has dimensions, number of rows and number of columns, equal to the dimensions that you see here on the outer parts of the matrices that we're multiplying. The resulting matrix is 2 by 1. In other words, it's a column vector with 2 components. Why is this a good idea? Well, it turns out that we're going to be able to understand linear systems by focusing just on the matrix, by focusing just on these numbers. Linear systems, the right-hand sides for these kinds of linear systems is just going to depend on what the coefficients of the x's and y's are in each of the components. That's going to allow us to then focus on this matrix and facts about this matrix to help us solve the system of equations. And that really is our goal here, is to ultimately solve this system of differential equations, to find its general solution which would then allow us to solve any initial value problem that we want. Of course, we have some nice technology that we can already use to solve the system, with maybe the word solve being in quotes. We can numerically solve it, and in fact, we don't even have to bother trying implementing Euler's method ourselves. We can go to the CD-ROM and go down to HPG System Solver, as we've done before. And I have this system typed in here right now. Negative 2x minus 2y is the first component on the right-hand side. It's what the x dt equals. Negative 2x plus y is the second component of the system, or the second component of the right-hand side of the vector field. It's what dy dt equals. And, well, we could certainly go up to the phase plane on the upper left-hand side and just get the computer to draw out a bunch of solutions. I'll just do that blindly here. Just pick a bunch of different initial conditions and follow those. It looks like we've got some solutions that in this phase plane head off upwards and to the left. If my initial condition is down over here. If I go further down, though, watch what happens. It goes downward and to the right as t increases. I'll try some initial conditions up in the first quadrant now. Those solutions go up and to the left in the end as t increases. And if I go further down, now I get solutions that go down and to the right. And we'd want to draw in, if we were doing this by hand, we could put a picture of this, we could print it out, and we could draw in some arrows indicating the direction that the solutions move as t increases. It seems like something fundamental, perhaps, is happening in between here. Can we find an initial condition that doesn't go up to the left or down to the right? Well, through experimentation, it seems like perhaps there might be a point close to where this cursor is right now that might head toward the origin as t increases, but it's very sensitive. In fact, it can be proven that there is a solution that goes toward the origin, and that's in fact part of what we're going to try to accomplish here, but to do that will take more work. You can approach the origin in a similar way from the right. You can get very close to the origin, and in fact there are solutions that go straight toward the origin here as t increases. We can see the vector field behind it. In fact, it's going to be just the direction field. Probably should zoom in on that to see it better. See those little vectors. And you should be looking at that direction field and seeing how the arrows are pointing in the directions that the solutions moved as t increases. And I could draw some solutions on top of these, like that one. I could also see vectors in the actual vector field. I can go over to the right and click Draw Vectors instead of Draw Solutions. And now if I go back to this direction field, no matter where I move my cursor, you see a vector that really is the true output of the vector field at the point that the cursor is pointing at. Notice that you get some pretty long vectors. Some of these vectors are very long because the velocity of the solution curve is going to be very large at those points. Some, near the origin, result in very small outputs from the vector field because the solution curves have a small velocity near the origin. I could draw in a bunch of these, but it's not real enlightening unless you do it carefully because of the fact that the lengths of the vectors kind of mess up the picture. That's why the direction fields are ultimately the more informative thing as far as drawing an accurate phase plane diagram. Before I go back to trying to think about this by hand, this system by hand, I want to notice two things. there are certain initial conditions where the vector in the vector field seems to point basically straight away from the origin, like right about there. And there are also points in the vector field, like right about there, where the output from the vector field points straight toward the origin. The ones where the vector field points straight toward the origin, in fact, correspond to those solution curves that do end up going straight toward the origin as t goes to plus infinity. And in fact, the ones that go away from the origin correspond to solution curves that, well, they go away from the origin as t increases along a straight line, but they also go toward the origin as you let t go to minus infinity, as you let t run backwards in time. Those are going to be straight line solutions. Those are going to be the key solutions that will help us find, ultimately, the general solution and understand what the vector field is telling us. So I want to get to the point where we can find those straight line solutions. But before we do that, perhaps it would be a good idea to find what we almost always find when we first encounter a system, to find any equilibrium points. Set the right-hand sides, as usual, equal to 0, and solve the resulting algebraic equations as a system. Negative 2x minus 2y was the first component of the right-hand side. Negative 2x plus y was the second component. There are a couple different ways you can solve the system of equations. For example, we could multiply the first equation by negative 1 and add it to the second equation to get rid of the x's, to eliminate the x's, which would give us y, and then we substitute back in to find x. We also can do substitution right away. For example, we can take this second equation and solve it for y in terms of x to get y equals 2x. Substitute that expression into the first equation in place of the y. This is a system of equations. We want both equations to be true at the same time. So we've got to do that if we're going to find any solutions. Simplifying this, we get negative 2x minus 4x equals 0, or negative 6x equals 0, which implies that any solution has got to have an x-coordinate of 0. And in fact, now going back up here, we can use the fact that y equals 2x to say that any solution is also going to have y equals 0. So the only possible solution to the system of equations is at the origin, x comma y equals 0, 0. And in fact, that definitely is a solution which you can check by substituting back into those equations. So there's a unique equilibrium point at the origin, 0, 0. Turns out, and I want you to read about this in the book, that if you focus on the matrix A, capital A, and if you write the entries of A like that, as little a, little b, little c, little d, it turns out that the algebraic equation, which I'm going to write in vector form, is ay equals 0. In scalar form, that would be ax plus by equals the number 0, and cx plus dy equals the number 0. This is going to have the origin, the 0 vector, as a unique solution. That's an algebraic equation, not a differential equation. If and only if AD minus BC is not equal to 0. The product of the upper left-hand and lower right-hand entries of the matrix minus the product of the upper right-hand and lower left-hand entries does not equal 0. That quantity has a special name. It's called the determinant of A, and we write it as det A, but say determinant, don't say det. The determinant of A is not equal to 0. That's going to be when this algebraic equation has the origin as its unique solution. That has a consequence for differential equations. The consequence for differential equations is that a linear system like that, dy dt, this is a y in case you can't quite tell, with an arrow, a little half vector on top of it, dy dt equals ay, has 0 as its only equilibrium point if and only if the determinant of A is non-zero. Which the determinant again is AD minus BC. Little a times little d minus little b times little c. These ideas actually have analogs for higher dimensional systems, 3-dimensional, 4-dimensional, n-dimensional. The thing that gets more complicated in those cases is the determinant is a very complicated kind of expression once you get past 2x2 matrices. Well, we will focus on that 2x2 case. So we found that the origin is the only equilibrium point for our system, and in fact, for any linear system, just checking this determinant would help you determine whether or not the origin is the only equilibrium point or not. If the determinant is 0, then you're going to have, in fact, infinitely many equilibrium points. They will either all lie on a straight line, or in fact, in the trivial case where the right-hand side is 0 in both components, the entire vector field is the 0 vector field, then in fact every point in the whole plane is an equilibrium solution. But that's not very interesting. All right, so that's what we do first. The second thing we want to do now is we want to find these straight line solutions. I'm going to go fairly quickly here, as this video is already getting fairly long. I will be making more videos with more examples. In fact, by the time you're watching this, I already have made such videos that you can look at, where I'll go through these steps in more careful detail. But here's the key. We're looking for straight line solutions. Ultimately, what that means is we're looking for vectors. We seek vectors v. In fact, I'm going to say non-zero vectors v, such that, this is one of the most important things in the whole course right here, such that this is true. A times v, we're talking linear system here, equals a scalar multiple of v. The traditional letter used for the scalar is the Greek letter lambda. We seek non-zero vectors v such that a times v equals lambda times v, where again our system is dy dt equals a times y. Such a vector is called an eigenvector, and such a scalar, lambda, is called an eigenvalue. Eigenvalues and eigenvectors are going to be very important for us, as you will see. Turns out that the best way to try to find the eigenvalues and eigenvectors is to think of this equation in the following way. I guess I don't need parentheses here. Subtract lambda times v from both sides of the equation, and then think of v as I times V, capital I, where I is the so-called identity matrix. It's a matrix such that when you multiply times any vector, I'll call that arbitrary vector y, you get that vector back. And you can check that. Once I've done that, then I can factor out the v from the left-hand side. Like that. And here's another very key observation. This is just another matrix. In fact, in our case, it would be a 2 by 2 matrix. Times a vector equaling the 0 vector. It's just like the situation I described in the previous transparency. That kind of algebraic equation right there, except with a different matrix. Instead of an A, it's A minus lambda I. But I've got an unknown vector y there and there's a 0 vector on the right-hand side. It's a homogeneous equation. And since we seek non-zero vectors v that solve this equation, we in fact want to seek values of lambda that make the determinant of this matrix equal to 0. I'll say that again. Since our ultimate goal here is to find non-zero vectors v that make this equal to 0, we want the determinant of this matrix to be 0. We don't want it to be non-zero. We want it to be 0. So in effect, we want to set the determinant of this matrix equal to 0 and solve for lambda. Now I forgot one thing here that you might be confused about. In fact, you should be confused about if you are paying close attention. Why in the world do we want to find such vectors? And this is what I'll end with. Okay? Well, there'll be a couple more things that'll be very quick. Why in the world do we want to find such vectors? The reason is this. A times v is the output of the vector field. If I'm thinking of v as being an arbitrary vector or an arbitrary point in the plane. A times v is the output of the vector field at the vector v. Come back to the screen over here and look up in the upper left-hand corner. The v you want to think of really as being a point that you're plugging in. It's where the black cursor is. That's v as a point. I could also associate it with a position vector which is based at the origin. That would go directly from the origin toward that black cursor. That's v. The green vector that you see that is based at the point the cursor is at is the output of the vector field. That's A times v. Straight line solutions have the property that v, the position vector from the origin to the black cursor, is parallel to A times v. Say that again. Straight line solutions have the property that if you start in a straight line solution with an initial condition there, call that starting place v, and think of a position vector going from the origin to that cursor there. You're going to be on a straight line solution if that position vector v is parallel to the output A times v of the vector field, parallel to the green vector. And if the green vector is pointing straight away from the origin, that's going to be the case. I'm going to be at a vector v where A times v is parallel to v. It's equal to lambda times v for some scalar lambda. And over here, if I go toward the ones that go straight toward the origin, the output of the vector field there is also parallel to v, but it's pointing in the opposite direction. The scalar lambda in that case would be negative, whereas the scalar lambda in this case would be positive. let's come back to the screen and very quickly wrap up. Ultimately, what we're going to see is once we've found lambda, then we will solve for v also. And it turns out that the function e to the lambda t times the vector v, this is really a vector-valued function of t, will be a solution to the differential equation. That's one thing we'll see. And for 2x2 systems, we'll typically get two distinct lambdas, two distinct eigenvalues, which will lead to two linearly independent eigenvectors that don't point in the same direction. And by adding what's called a linear combination of those solutions, we'll get the general solution. But I won't go into details just at the moment. All this algebra has reminded me of a quote from Thomas Jefferson. I want to zoom in on this. Talking about math, actually, Thomas Jefferson once said, he was thinking of math in terms of calculation, he says, the science of calculation also is indispensable as far as the extraction of square and cube roots, algebra as far as the quadratic equation and the use of logarithms are often of value in ordinary cases. And here's the downside, according to Jefferson, but all beyond these is but a luxury. A delicious luxury indeed, but not be indulged in by one who is to have a profession to follow for his subsistence. Okay, so what is Jefferson saying there? You know, well, basic math is certainly useful. And while higher math might be lots of fun and beautiful, which I would agree with, most people can't make a living on it. Well, just to encourage you, this was said 200 years ago. There were some people who could make a living just doing math back then. Those were the professors who were supported in the research universities and by benefactors. But nowadays, engineers, scientists, they need to know, you need to know, a lot of algebra, including matrix algebra, beyond just the basics, if you are going to be out there in the world doing real valuable, cutting-edge scientific and engineering work. This really is valuable for you, and I'll end on that note of encouragement.